Okay, how do we delete then? Delete also means removing. Well, where do we want to remove? We want to remove the minimum ordering value. So how do we do this? Well, a little more complicated. First, we swap the data between the root and the most recently added leaf node. Why do we do that? I'm going to draw a small tree this time because I don't want to spend the whole time drawing trees. When we remove, why do we want to swap between the root and the most recently added leaf node? Well, what's the most recently added leaf node? It's this guy. If we swap these two, we can then remove this guy. And watch this. We still have a complete tree. So that's what we do. We remove the most recently added leaf node, but then our heap could be out of order again. So now we have to restore the heap, this time via downheap bubbling. So swapping the key value pairs is easy. Now we have to remove the most recently added leaf node from the heap. Okay, that's not that big a deal either. We just have to grab the data from the inside of the leaf node, right? Because we've done the swap already. Grab it and hold it. That way we can return it later on. Set the leaf node's parent to none, and then set the appropriate child of the parent to none. Basically, we sever the link, just like we did with removing from a linked list. And then we downheap bubble. So this is, via downheap bubbling. This is like upheap, but a little more complicated and in reverse. Now, why is this more complicated? Well, with upheap bubbling, we only had to worry about the parent. But downheaping has to account for either child. Right? It could go left, could go right. So our algorithm's a little more complicated. We start with the root, and then while the current node is not the leaf, right, we're going the opposite order. If the leaf has no children, so we don't need to do anything. Well, the current node is not the leaf, and the relationship between the current node and either of its children violates the heap order property. Then we swap the data from the current node and its child, which fulfills the heap order property the most. So we might have two children that are violating the heap order property. So we have to find the minimum of the two. The min key and the min heap, the max and a max. And then we move the current node to the child node and that we just swapped with, and we continue. So let's do some examples. Okay. We have our heap. What happens when we remove an element? Well, first thing we do, and I'm going to pause for a moment so you can pause and try it on your own. First thing we do is we swap the root and the leaf. So 1 comes here, 7 comes up here. We then pull 1 and its associated data out for returning later on, and we axe this child node. Okay, so now that's gone. Cool. And now we do our heap order property. So 7. Well, is 7 a leaf? No. Okay, let's compare it. Well, it's both of these violate the heap order property. Which one are we going to use? Well, 4 is the smaller of the two, so let's use 4. So we swap 7 and 4, and 4 comes up here, and 7 comes here. Now we do it again. Is it the leaf? No. Is it violating the heap? Well, 7 and 7, these are fine. This is a cool situation, but this is no good. So we do it again. We kill the 6. We swap the 6 and the 7. Is it the leaf? Is it a leaf? No. Is there a violation? No. We're good. And now we can take this and kick it out and return it. And there we go. 4, 6, 7, 11 down that line. Okay. What happens when we do it again? Well, pause if you want to try it yourself, but we swap and then we destroy this. So 11 comes up here. Well, now this time we go right. So 5 comes up here, 11 comes here. Well, check again. 6 comes up here, 11 goes here. What happens if we do it again? Let's try this. What happens if we do it again? Well, now we have to swap with 8. So 8 comes up here. And this goes away. Now which way do we go? Well, we got two options, right? We can go left, or we can go right. Let me choose blue because blue is going to be friendlier for color blindness. Okay, so if we go left, what happens? Well, if we go left, 6 goes to the root, right? And we'll call this 6L and 6R. These have no meaning other than so we can keep in mind which one's which. So 6L goes to the root, 8 comes to here. Well, 7s are both violating again. So now we're probably going to go left again because we went left the first time. Anytime there's a tie, right? This is an algorithm. So what we're probably going to end up is with a tree that looks like this. Boom, 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 boom. Okay. If we go right, 6R is going to bubble to the top, right? And bubble, I'm using this term. This is where bubble sort kind of becomes a thing, right? We're bubbling like in bubble sort. So 8 goes here, and then we're good because 8 is greater than 11. So we don't have to worry about that order. So we can go 6L. Now, why am I doing this? And here's why. I want to show you. Let's remove one more from each of these. If we remove, again, from 6R, we're going to come down here, and 11 is going to bubble to the top. 11 comes up here, right? And this goes away. This leaf goes away. Well, what's going to happen? 11 is going to go left, and 6L will come to the top. 11's at this spot now, and we went right the first time, so we're probably going to go right again. So we're going to end up with a tree that looks like this. If we did left the first time, right? Okay, same thing. This guy comes to the top. 6L gets removed. Well, what happens? Well, we come up here. 11 comes up here. 6 is less than 7, so 6R comes to the top. 11 comes here. 7L stays. 8 and 7R stay where they are. So it doesn't matter. Either way, whether you go left or right, the result's going to end up with a 6 at the top for the next 2 iterations. This process makes sure that the minimum key is at the top, something with the minimum key. And if you'll notice, in each of these trees, the next to minimum key is guaranteed to be one of the children of the root. So the next time you bubble, it's going to go up the chain, right? I say this to say, it doesn't matter whether the default setting is that you go left or right. It really doesn't matter, okay? Either one is an acceptable option, and you just saw why. Okay. And you can see here, notice that 7R, 7L are both in the next spot. So if we remove our 6 or our 6, a 7 is going to be at the top, but notice it's a different one. This is why that arbitrary order is important.